Hello friends, in the last lecture we began considering certain concepts that are associated with the materials in the atomistic scale. We were looking into the arrangements of the atoms in a crystalline material, the ones that we are interested in, particularly metals and alloys, and we were attempting to rather describe a plane in the regular arrangement of the atoms, or a representation of the regular arrangement of the atoms. The reason we are interested in these because we have been considering the mechanical behavior of metals and alloys or starting from a graphical representation, and we saw that their behavior can be categorized into elastic and plastic behavior, and this behavior depends on the mechanical condition that we impose. And even though we impose a uniform mechanical condition, the plane that constitutes a given material, depending on its inclination, and even within the inclination, even within the given plane, given the orientation of the direction, the mechanical condition experienced would vary, and correspondingly the response offered by the material would vary. Now, so far when we have been discussing or describing the plane or the direction, we have used the Cartesian coordinate system. However, when we move into the atomistic scale, it allows us rather to describe these plane in a unique way that is rather associated with the nature of the arrangement of atoms in a given material. So we were able to provide a material specific description of a plane and the direction. So that is one of the reasons why it is rather quantitative when we describe the mechanical condition in the atomistic scale, because we have rather a material based description of the plane and the direction along which the mechanical condition is being imposed. Now, when we consider the crystalline material, we saw in our last lecture that owing to their crystalline arrangement, it is possible for us to represent it in the form of a unit cell. And the uniqueness, when we want to use the unit cell to describe a given material, we need to take care of two things. The two parameters or two features characterize a unit cell. One is the shape of the unit cell, and other is the position of the atoms in that unit cell. Now, when you consider the shape of the unit cell, we have two parameters to describe it. We have the lengthwise parameters and the angular parameters. And these lengthwise and the angular parameters are rather associated with, even though it looks like the Cartesian coordinate, in this case it is referred to as the crystallographic axis. So both the lengthwise parameters and the angular parameter are associated with the crystallographic axis, and based on these crystallographic axes, we are able to describe the A, B and C and alpha, beta and gamma, and this particular shape, it corresponds to cubic crystal system. So what essentially we are doing is we are considering, so far we have been focusing on the cubic crystal system, and this cubic crystal system is rather one of the crystal system that is widely associated with, or that is in a way the materials or atoms in a given highly applicable materials are arranged. So therefore we started our discussion with the cubic crystal system. Now, before getting into the positions of the atom in the cubic crystal system that would eventually render us different crystal structures, we began describing the different planes within this cubic crystal system, and we saw that there are three different distinct steps that are involved to describe a plane in a unit cell, and that involves identifying the intercepts first, identifying the point where the plane intersects with or plane meets the crystallographic axis, and then that's the first point, identifying the points, and the second point is to take the reciprocal of it, and finally it would be to factorize it. So these are the three steps that are involved to describe a given plane within a unit cell. Now we saw that the reason often we take the reciprocal of it and factorize it is because we want to avoid fractions while describing the plane. So therefore we take the reciprocal of it and factorize it. And now when you consider a given plane in a unit cell, geometrically there are other planes that are similar to it, that are equivalent to it. For instance, if you consider the plane in the red, this plane represents the face of an unit cell. So therefore geometrically there are several other planes that are equivalent to it. So this one is a similar plane, this one is a similar plane. So there are 6 different planes that are geometrically equivalent to it. Geometrically equivalent meaning the orientation, or the rather the way we describe these planes. So in this case we describe it as the face of the unit cell. So all these ones that are highlighted or that are marked as in red cross, they are also the face of the unit cell. So these are geometrically equivalent. So all these geometrically equivalent grains, we categorize them as the family of planes. Besides geometrically being equivalent, there is also the possibility of being crystallographically equivalent. That we will come in a moment. Before the end of the lecture, we will look into it. But this, when you just consider the geometry of the unit cell, the faces, or rather the planes that are highlighted in red, they form a family of planes, and these family of planes are rather represented by H, K and L that are enclosed in a flower bracket, and these are referred to as the Miller indices. So the Miller indices for one plane is represented, or it is identified, or it is described by these three steps, and it is enclosed in a bracket, in a curved bracket or parenthesis. And on the other hand, the family of planes, the geometrically equivalent planes, are represented using the flower brackets, and these are referred to, and again the Miller indices are referred to or enclosed in the flower bracket. And all these planes within that are enclosed in the flower bracket, all these different planes that contribute to the family of planes, they are geometrically equivalent. Now, one other way of understanding the family of planes is, given the nature of the unit cell, given the nature of the cubic unit cell, it is possible for us to create the entire system by placing the cubic unit cell on the top, on the either sides, and front and back. So it is possible for us to create the entire material that exhibits, or that is of a cubic crystal structure, by placing this unit cell along this direction, that is along the left and right direction, top and bottom, and back and front. So it means we can create a continuum, we can create a material, we can create a three-dimensional sample starting from this unit cell and repeating it in all the directions. Now, the reason or why we need to consider this is because when we are able to create the entire macroscopic material by just repeating this unit cell in all the possible directions, it allows us to place our center, the origin of the crystallographic axis, in any point of this unit cell, in any corners of this unit cell, because of this nature of this cubic unit cell, because that it is a cubic unit cell and we can create the entire continuum, the entire material, by arranging it in, or by replicating it in in all the directions possible. It means that whenever I shift my origin for the crystallographic axis from this point, that is initially it is here, and it is possible for me to shift here, here, here and here, all this means the same. It is all, they are equivalent, because again it is owing to the nature of the unit cell. It is cubic unit cell, and it is possible for me to create the entire system by arranging it, by replicating it in the directions, in all the directions, and therefore all these points can act as my origin for the crystallographic axis. Now, when I shift my origin from this point to other points, the same plane can be described using different Miller indices. So the same plane, the one highlighted in red, the one shaded in red, can be described by considering my origin at the different points. So all this Miller indices that describe a given plane while we are changing the origin of the crystallographic axis are also enclosed in the family of planes. So the family of plane, they capture all the geometrically equivalent planes, one aspect. So they capture two aspects. One is they gather all the geometrically equivalent planes. Secondly, they express a given plane in an invariant manner, meaning if you are considering a plane, and irrespective of where your origin of the crystallographic axis is, and which one you are taking as the positive coordinate or which one you are taking as the negative coordinate, irrespective of how you are defining the crystallographic axis, when you are considering a plane, the way to describe the plane will be included in the family of planes. So you are considering a plane, and you are considering, so you don't know which point is going to be taken as the origin of the crystallographic axis, and which is going to be taken as the positive and negative coordinate. But when you have the family of planes, or when you have this plane represented as in the form of the family of planes, then essentially you will be able to encompass, you will be able to include all the possible indices that describe a given plane, irrespective of where the crystallographic axis is superimposed. So irrespective of whatever combination of the crystallographic axis is possible. So whatever, irrespective of where we are considering our crystallographic axis, where we are considering our positive and negative coordinate, the description of a plane, of a given plane, is rather included in the family of planes. So it serves both role. One is purely from a practical standpoint, it includes all the geometrically equivalent planes. From the theoretical standpoint, irrespective of what the nature of the crystallographic axis is, the way to describe a plane, a given plane, is included in the family of planes. Now, so this is our discussion regarding, this was our discussion regarding the planes and the family of planes. Now, one other dimension, one other aspect that we are interested in, particularly when we are considering the mechanical behavior of material, is the direction. So in addition to the plane, within a given plane, we have already seen that the stress that is experienced, the mechanical condition that is experienced by the material within a plane, it will vary along the different directions. So in order to understand the direction, again within the framework of a unit cell, wherein we have, instead of the Cartesian coordinates, we have our crystallographic coordinates, so crystallographic axis. So here what we are essentially trying to do is, we are trying to rather represent a given direction using Miller indices. So let us begin by considering the unit cell that is associated with the three crystallographic axes. Now, one way of understanding the direction is by considering a Cartesian coordinates that we are familiar with and describing a point in the Cartesian coordinate using a position vector. So we have a point O, and this point O we are describing it using a position vector R. Now when you consider a position vector R, so when you want to reach from this point, say from this point A to this point O. Now in order to do that, we are considering a magnitude. So if you want to move from this point to this point, you have to walk, and you have to walk a certain distance, and that certain distance should be in a specific direction. So we have a magnitude and the direction, so therefore we are representing it in the terms of a position vector. Now this position vector is often expressed as some A1, rather A1 I bar P1, or it can be A2 J bar. So what we have represented it is by expanding, this position vector can be extended into A1 I bar, or rather this is I, on top we have an arrow, and this is unit vector, and this unit vector is along, so this I unit vector is along the x direction, and the j unit vector is along the y direction, and the k unit vector is along the z direction. So this is I, j and k. So what we have done is, we have described a point using a position vector, and this position vector comprises of a magnitude and a combination of a magnitude and unit vectors, and each of these unit vectors, they are orienting towards the frames of reference that we have considered. So this is the way we describe a point in a three-dimensional space. Now the magnitude of this A1, A2, A3, the magnitude that describes the unit vectors, it is often estimated by projecting the point onto the corresponding axis. If I project this point onto the z-axis, this magnitude, this distance would be my A3. And now if I take this point here and then project it along the x and y axis, then this would be my A1 and this would be my A2. So what essentially we have done is, we have considered a three-dimensional case, we have considered a three-dimensional space, and in that three-dimensional space we have considered a Cartesian coordinate system, and we are attempting to describe a point in that Cartesian coordinate system, and this point we are describing it using rather a position vector. The position vector is associated with magnitude and unit vectors, three different unit vectors that are aligned along the direction of our Cartesian coordinate system, or the frame of reference here. And the magnitude associated with each of these unit vectors are estimated by, or they are determined by considering the position, or by projecting this point onto the corresponding axis. Now in the same way, the direction within so if you replace this axis, this Cartesian axis, with the crystallographic axis, And if you consider a point here, we describe this direction in the same manner. So first we consider if you want to rather describe this direction, we consider the point where this direction, or we consider the point associated with this direction, the end point associated with this direction here, and this end point or this direction is largely, or it is primarily restricted to the y-axis, and it does not meet the x or the z-axis. It is purely restricted to the y-axis. So that means the only non-trivial entity, or only non-zero entity will be the y1, and so it will be just y. So when you consider the point where the direction ends, that point is rather a, again assuming that we are considering the cubic system, so all these distances are a. So this point here, the magnitude associated with this particular direction, along the x-axis it is 0, along the y-axis it is a, and along the z-axis it is 0. And when you factorize and when you reduce this term by multiplying it by 1 by a, then it would be 0, 1, 0, and when it is enclosed by a square bracket, it depicts a direction. So motivation for rather describing a direction within a unit cell comes from the way we describe a point, position vector to describe a point. So what essentially we will do is, we will rather consider the direction, the point where the direction ends, and for that point we consider and we estimate the corresponding magnitude that is required, the corresponding distance that we have to move along these three different crystallographic axes to reach that point, and based on that we describe the direction. So in order to describe the direction, we need to have an endpoint, and we have to consider how we should move within the unit cell to reach that endpoint. So we should move a certain magnitude along the x direction, certain magnitude along the y direction, and certain magnitude along the z direction. Those things we need to figure out, and once we are able to compile all these magnitude, the distance that we have to cover in all the different crystallographic axes, then we can present it in the form of this point. That is we are just representing the magnitude associated with the direction, and then we can factorize it and we will end up with the direction, and the direction is rather represented by the square bracket. So again we have HKL representation, and this HKL representation, they are Miller indices, and these Miller indices are, when they are enclosed in the square bracket, they essentially mean the direction. Now we will consider one more or two more examples before we proceed. So if you consider this point, this direction along the that is indicated by a green arrow, so it ends at this point, and when you consider the way we have to move to within the unit cell to reach this point is, we have to move a units along the x axis and a unit. So again x is the crystallographic axis, not rather a Cartesian coordinate, and we have to move y. So we have to move x, a distance or a magnitude along the x direction and a along the y direction, and along the z direction we don't have to move at all. So therefore the corresponding magnitude is a and 0. Now when you factorize it, when you normalize it, you will get up with 1, 1, 0, and this is the Miller indices that represent the direction that is indicated in green within the unit cell that is shown here. Now it is possible for us to consider a direction of this sort, which stops somewhere in the middle, and all that you need to do is, again you need to find the end point of the direction, and when you find the end point of the direction, you need to consider how we should move along these crystallographic axes to reach that point. So this point in blue, we need to move a by 2 in the x and y direction, and also in the z direction we have to move a by 2. So to reach the end point of the direction in blue, we have to move a by 2 in the x direction, a by 2 in the y direction, and a by 2 in the z direction. And now when you take the product of 2 by a, what we would end up having is, we would end up having or representing this direction as 1, 1, 1. So we have this direction that stops in the middle of the unit cell, and that is represented by 1, 1, 1. Now if you consider a unit cell that is rather here. Let me take a different color. So if you consider rather a direction that is here, now the point that the one in the light green, the point where the direction in the light green stops is at this corner. So maybe I'll try to use gray. So we are considering this direction in light green and it stops at the corner of the unit cell. Unlike the one in blue, it stops at the corner of the unit cell. So when you consider the point that is associated with the corner of the unit cell, so in order to reach this point here, we have to move a distance along the x-axis, a distance along the y-axis, and a distance along the z-axis. So the initial points will be a, comma, a, comma, a, and when you normalize it, you will end up with the similar Miller indices. So these two Miller indices are similar. So what essentially we have is, we have two directions. So this is indicated in blue. So I'm just plotting the direction that is indicated in blue and the one that is indicated in green. So these directions are, even though the dimension of these directions are the same, or rather the dimensions of these directions are significantly different. We can see that the direction, the magnitude of the direction in blue is much less than the magnitude of direction in green, in light green. But when the direction alone is considered, apart from the magnitude, when you ignore the magnitude and when you consider the direction alone, both these are pointing along the same direction. So both these are equivalent to one another, and that's the reason they are represented by the same Miller indices. Okay, as opposed to the equivalency that we observe during a given plane, in case of directions, the equivalency is even more prevalent because we don't have to worry about the magnitude when we are considering the equivalent directions, because in case of equivalent directions, irrespective of the magnitude, if they are superimposed with one another, we will see that they can be represented using the same Miller indices, and therefore despite there can be, so these two directions, despite their differences, despite their noticeable differences in the magnitude, in the point where these directions terminate, because they are oriented along the same direction, they can be described using, they are described using the same Miller indices, and they are equivalent with one another. So this is one of the rather a distinguishing feature of the equivalency between the directions. So in case of the equivalency between the directions, the magnitude often plays a rather, particularly in a cubic unit cell. Of course, all these discussions have been restricted to cubic crystal structures. So in a cubic crystal structure, the unit cell associated with the cubic crystal structures, irrespective of the magnitude, when the two directions are superimposed, they overlap with one another completely, they indicate the same direction. Now, even though this is rather, we can understand it, and this is rather we can state that this is equivalency can be referred to as the geometrical equivalency, we will soon understand that in case of crystallographic equivalency, when you have these two directions, one pointing it in this direction, the other pointing it in this direction, the one pointing in black, the other pointing in red, we will soon understand that in the crystallographic setup, in the context of crystallography, when we are considering the the equivalency from, or crystallographic equivalency of two directions, these two directions will also be equivalent. So two directions pointing along the same, having the same orientation but different magnitude, it is equivalent because they are pointing along the same direction. However, when you consider crystallographically, these two that are pointing in the same opposite direction but completely overlap with each other, crystallographically they also are equivalent with one another. And similar to all the features, similar to the features that the aspects of the family of planes, that is the family of planes, they collect all the geometrically equivalent, they represent all the geometrically equivalent planes, and also they give us rather a holistic representation irrespective of the origin on the nature of the coordinate system or the origin and the nature of the crystallographic axis. The same goes for the family of directions. So the family of directions are represented by this bracket here. So this representation, it means we are considering the family of planes. So this family of planes, it includes all the geometrically and crystallographically equivalent directions, and on top of it, it also helps us describe or it also includes the representation of a direction irrespective of the way we have selected the way we have described our crystallographic axis. Now, so this discussion has so far been confined or rather restricted to that of the cubic crystal structure. And we saw that the feature of the cubic crystal structure, the characteristic feature of the cubic crystal structure is A, B and C. That is, the lengthwise parameters along the crystallographic axis, they are equal, and the angle subscribed by between the crystallographic axis, they are of 90 degrees. So this indicates, rather, this describes the cubic crystal structure. So this is of a shape, this offers a shape to the unit cell, and that is of a cubic crystal structure. Now, one other crystal structure that is prevalent among the metals and alloys that are highly applicable is the hexagonal crystal structure. Now, the characterizing feature of this hexagonal crystal structure, that is the way we describe the hexagonal crystal structure using these parameters, is two of the lengthwise parameters are equal but not the third, and in addition to that, two of the angular parameters are 90 degree, while the third one, it is not equal to both these and it assumes a specific angle, that is 120 degree. When these conditions are satisfied, what we have is what we are talking about is an hexagonal crystal structure. And when you represent the unit cell that is associated with the hexagonal crystal structure, it is often of this form here, or a better way of writing it or better way of drawing it would be to begin with the corresponding crystallographic axis. And it is important for us to note that even though these two angles are 90 degree, so this is 120 degree. And you have your face here and the other face here. And what we have now represented is the unit cell of the hexagonal crystal structure. So this is a unit cell of the hexagonal crystal system. So we have A, B. So A is equal to B, but it is not equal to C. So A and B are equal, but it is not equal to C. And the angle between, so these two angles are 90 degrees, and this angle is 120. So this is the way of representing the hexagonal crystal system, or the unit cell that represents the hexagonal crystal structure. Now, the reason I'm not comfortable using crystal systems now is because we have not considered the position of the atoms. Only when we consider the position of the atoms, the crystal structure will be the more appropriate term. So far we are just considering the shape of the unit cell, and for a given crystal system, how the shape is varying, that's exactly what we are looking into. So for the hexagonal crystal system, this is how the shape of the unit cell will look like. Now, since this angle, unlike the cubic unit cell, since this angle is 120 degree, there is one difficulty in building the entire material from this unit cell. What I mean by that is, when you consider the cubic crystal system, we saw that when you place the unit cell of the cubic crystal system in all the direction, you will be able to, in all possible direction, you will be able to build a continuum. However, since here the angle is 120 degree, when you place this unit cell in all possible direction, we will not be able to build a continuum. The expected continuum we will not be able to build. So therefore, when we want to build a continuum out of this unit cell, we have to first club a 3 unit cell in a specific way, so that it gives a specific arrangement of the unit cell that can subsequently be replicated to create a continuum. So what essentially we are interested is creating a continuum from unit cell, translating the unit cell into a continuum, meaning into a continuous material. So in case of the cubic crystal system, all you have to do is you have to replicate the cubic unit cell in all the possible direction. That will create a continuum. However, in case of the hexagonal cubic cell, first you need to build a pseudo unit cell. Again, that is not the conventional name, I'm just giving it a name. We need to build for this unit cell, we need to build a pseudo unit cell. And only by repeating the pseudo unit cell, you will be able to build a continuum. This pseudo unit cell, it comprises of 3 such the fundamental unit cell. The pseudo unit cell, it comprises of 3 such fundamental unit cell. By repeating this fundamental unit cell alone, you will not be able to establish a continuum. You will not be able to, by translating, or you will not be able to translate a unit cell to a material. By just replicating this unit cell as it is, you will not be able to rather establish a continuum. You will not be able to rather establish a material. However, when you translate this to a pseudo unit cell, you will be able to do it. So let us see what this, again, this you would already have seen. I'm just giving you a new perspective into how to consider these unit cells, particularly the hexagonal unit cell. Now it's a bit tricky for me to draw this, but let me give it a try. So yes. So what we are creating is, we are creating rather a pseudo unit cell, which when replicated in all possible direction will yield you the continuum. The fundamental unit cell will not do that for you, but this one will do that for you. So now if this is the center point, now each of these are rather the individual unit cells. Each of these are rather the individual unit cells. So if you consider these, this is an individual unit cell, this one is an individual unit cell, finally the one in the blue will be an individual unit cell. So we need to have 3 different fundamental unit cells in order to construct the hexagonal closed-packed structure that we are familiar with. So when you consider the unit cell entirely, this is how it looks like. We need 3 different unit cell, the fundamental unit cell, fundamental entities, when we want to rather create the hexagonal structure that we are familiar with. And now this hexagonal structure can be repeated infinitely and the corresponding continuum can be established. So this hexagonal structure here, so this structure here now has the property of the cubic unit cell. This representation, this pseudo unit cell has the property of the cubic unit cell, meaning, so this pseudo unit cell has the property of cubic unit cell, meaning it now can be expressed in a way that now this pseudo unit cell, the pseudo unit cell that pertains to the hexagonal crystal system, can be repeated similar to that of the cubic unit cell to translate the unit cell into a continuum or the macroscopic material. So now when we have such a pseudo unit cell that has the property of the cubic unit cell, then it is rather ideal for us to describe the crystallographic axis based on these pseudo unit cell. So this has become quite messy because we have just wanted to show the 3 different fundamental unit cells that contribute to this pseudo unit cell here. But now when you have such a setup, when you have such a representation of your unit cell that has the property of the cubic unit cell, meaning this can be repeated and the repetition of it will yield you the required, will yield us the required material. In such a case, it is ideal for us to have crystallographic axis and parameters associated with the crystallographic axis in a way that is based on this pseudo unit cell. So therefore, if you consider, or if I draw this properly, so what we have done is I have repeated or reconstructed this pseudo unit cells that we have considered. And when you consider this pseudo unit cell, and now this pseudo unit cell is similar to that of the cubic unit cell because it is possible for us to repeat this unit cell and then arrive at a continuum of material. Now when you consider these 3 unit cells, it is rather beneficial to us if we have our coordinate axis set up based on this unit cells, based on this pseudo unit cell. So therefore we are considering a coordinate axis that includes all the 3 different unit cells that make this pseudo unit cell. So what essentially we are doing is, we have three different unit cells that make up this pseudo unit cell. So now we are defining our crystallographic axis in such a way that it includes all the three unit cells that make this pseudo unit cell. So we have a common baseline here. So this would be one of our crystallographic axis. So we have another crystallographic axis here that includes the unit cell 1 and 2. We have another crystallographic axis here that includes the unit cell 1 and 3, and we will have another axis here that includes our unit cell 2 and 3. So this axis here, it includes all the three unit cells. This axis here, it includes the unit cell 1 and 2. This axis here, it includes the unit cell 1 and 3, and this axis here, it includes the unit cell 2 and 3. So we have created a unit cell, or rather created a crystallographic axis that encompasses all the three different unit cells that is required to build the hexagonal unit cell that has the property of the cubic unit cell. So now the crystallographic axis, instead of having 3 coordinates, now has 4 coordinates, and the fourth coordinate, we need 4 coordinates because we are not considering a simple unit cell, a fundamental unit cell. We are rather considering a complex unit cell that comprises of a complex pseudo unit cell that comprises of 3 different fundamental unit cells. And that's the reason, since we now have to have a coordinate axis that includes all the 3 unit cells, we have 4 coordinate. We have a coordinates axis that comprises of 4 axes. Now these 4 axes are referred to as, or they are represented by H, K, I and L. And the I here, I here is the axis that comes from this axis here, that is a part of this axis here. The I is a part of this axis here, and this again the additional axis that comes from the nature of this complicated unit cell that we have built because of its relevance to the cubic unit cell, and that is represented by minus of H plus K. So this is how rather we represent the coordinates axis that is associated, that is needed to describe the planes and the direction in an hexagonal system. So whenever we describe a plane or a direction using the fundamental unit cell, it gives us H, K and L. Now from this H, K and L, it is possible for us also to estimate the newly included index for this particular crystal structure. Now these indices that includes I as well, these indices that represent or that is required to describe a plane or a direction or a point in the pseudo hexagonal unit cell that comprises of 3 fundamental unit cells, these are referred to as the Miller-Bravais indices. So what we have is, in case of hexagonal unit cell, the hexagonal unit cell as it is, because of its shape, cannot be treated as the cubic unit cell, and so we need to have, so we built a pseudo unit cell that can be treated as the cubic unit cell, and that is by clubbing 3 fundamental unit cells together. And when we do that, the existing crystallographic axis is no longer relevant to us, it is no longer useful to us. So what essentially we do is, we consider an additional crystallographic axis so that all the 3 included unit cell, the fundamental unit cell, are being considered. So when you have 4 crystallographic axes, all the unit cells that we have considered are included in the representation. Now, the reason why we need to consider a unit cell that is similar to that of the cubic unit cell is because only when we have a nature that is similar to that of the cubic unit cell, only in that case we have the possibility of shifting our origins in such a way that the family of planes, or we can handle the crystallographic axis in such a way that we are able to make or represent a given plane in an invariant manner. So we saw that while considering the cubic crystal system, we saw that it is possible for us to shift rather all the points, all the crystallographic axes that we make based on the points, of the points in the crystal system. The unit cell is rather equivalent because we are able to rather reconstruct the entire continuum from a given cubic unit cell. Owing to this nature, we can place our origin of the crystallographic axis at any point, and that would be acceptable. So it will be equivalent, and we can describe any plane or a point using or placing the origin of the crystallographic axis at any point. Now, when we consider the fundamental unit cell of the hexagonal unit cell, then we cannot do the same. We cannot place the origin here, and here. We cannot place the origin here and then expect an equivalent description of a plane or a direction. We cannot equivalently, or we cannot have an invariant description for this type of a representation, this type of a hexagonal unit cell. However, when you construct a compound unit cell that comprises of the fundamental unit cells, when you construct such a compound unit cell, then using this compound unit cell, then it becomes possible for us to describe the family of planes or the family of directions in an invariant manner. So whatever we have considered in the cubic unit cell will be applicable to the hexagonal unit cell only when we are able to create such a compound unit cell. So that's the reason we construct a compound unit cell, and when we construct a compound unit cell, we create we introduce 4 crystallographic axes, 4 different crystallographic axes. So that's the reason why we move from the fundamental unit cell to that of the compound unit cell that we have considered so far. So once we have created the compound unit cell, and once we have represented our planes and the directions using the Miller-Bravais indices, instead of just Miller indices, once we describe our plane and direction using Miller-Bravais indices, then what essentially we mean is whatever understanding we have gained for the family of planes and family of directions for the cubic system can directly be adopted to the compound hexagonal crystal structure, compound hexagonal unit cell. So that's the reason we take the pain of creating such a representation. So theoretically, that's the reason why we take the pain of representing the crystallographic or the unit cell of hexagonal structure in this way rather than just the fundamental unit cell, because all the understanding that we have gained for cubic can directly now be adopted to this, because this unit cell, when repeated in all the directions, will give you the continuum of the material that we want. So when this unit cell is repeated, this gives us the material that we want. Now, so far again we have considered just the shape of the unit cell that represents the crystalline arrangement of the atoms in a material. So all that we have been focusing on is just the shape of the unit cell. What we have not considered is the atomic positions. Now, for a crystal structure that has its unique shape, depending on the position of the atoms, the arrangement of the atoms in a given material would vary. So what I mean by that is, so when you fix the shape, when we fix the shape by stating all the lengthwise parameters are equal and all the angular parameters are equal to 90 degrees, we arrive at a cubic crystal system. And only when I place my atoms, only when I consider the position of the atoms, then I will be able to describe my crystal structure. So now the cubic unit cell that pertains to the cubic crystal system will be of this form here. And now I can consider positioning my atoms, and when I position my atoms in these corners, what ultimately I would end up having is, so all that I am doing is I am considering the corners and positioning atoms, and all that I would end up having is creating a simple cubic crystal structure. So far our discussion has purely been theoretical. We have focused on the shape and we have been discussing purely theoretically. Now we have positioned atoms, and this now becomes a crystal structure, and there are materials, and the arrangement of the atoms within the materials can be represented by this unit cell. So one example is polonium. I hope the spelling is right. So when you consider the material, a bar of polonium for instance, and when you consider the arrangement of atoms in the bar of polonium, And that arrangement of the atoms can be represented by this unit cell here, because in addition to the shape of the unit cell, we have also now considered the positions of the atom. So it belongs to the simple cubic crystal structure, and that is represented by this unit cell here. Now, when you consider, so supposing you are viewing from this direction. So you are viewing the crystal structure from this direction. So this is the direction we are viewing our crystal structure. So let us now try to define this direction. So when I say that we are viewing from this direction, so this direction and this direction are equivalent. So this direction and this direction are equivalent because again they are oriented in the same way, so they are parallel to one another. And now let us try to describe it. Now if I want to describe this direction, I need to place my origin at this point, and let us assume that this direction meets, so this direction is this one. So the one that is in red is equivalent to the direction that meets the atom, and that is so we have considered our origin to be in the blue point. So this is our origin now, and let us assume that this is our x-axis, this is our y crystallographic axis, this is our z crystallographic axis. Now this direction would be, and let us assume that the positive quadrant of the y-axis is along the red direction. The positive quadrant of the y-axis is along the z direction, the positive side of the y-axis. Again, we are free to assume that because we have understood what the family of directions represent. So we are free to assume that. So when you consider this direction, it is exclusively associated with rather the y-axis alone. So the x component is 0 and the y component is a, and you normalize it, you will end up with 1, and the z component is 0. So this is the direction, and when you consider the family of direction, it will be rather 1 0 1 0. So all the directions that are included in the family of directions, they are equivalent and they indicate this direction. So all the directions, all the Miller indices that are included in the family of direction, they are equivalent and they indicate this direction. Now when you view in this direction, the plane that you observe, when you view along this direction, the plane that you observe, when you view along this direction, the plane that you would observe is this plane here. So this is the plane that you would observe. When you view along this direction, when you stand here and view along this direction, you would observe this plane. And this plane with respect to our new coordinate system, it is again with respect to our blue new coordinate system, this the plane in green, it rather is, it touches only the y-axis, but the x-axis it is parallel, and to the z-axis it is parallel. So it is, if we assume that it touches along in the infinity, so when you take the reciprocal, it becomes 0 and 0. So what essentially we have ended up is, we have now represented the plane that is visible when you are viewing along the specific direction. Now as you can see that the indices associated with the direction and the indices associated with the plane are the same. So essentially this gives us a relation how when we are representing an index, or when we have a specific Miller index, and the same Miller index is used to describe the plane, and the same Miller index is used to describe a direction, there is a specific relation associated with it, and this relation is what we observe here. Now the reason why we started off with this is because when you observe it, when you observe from this direction, this plane is visible, and beyond that all the planes, when you consider the plane beyond this, the atoms, when you extend this unit cell, the atoms, the position of the atoms superimpose with the existing atoms. When you extend beyond this, they superimpose with the existing atoms. So all that you would observe is when you look at this plane by standing or by in this along this direction, when you consider this plane along this direction, all that you would observe is 4 different atoms, and the atoms, all that you observe is would be a plane, and this would be the position of that atoms. Now the atoms behind this particular plane, so these atoms will have the position identical to the atoms that we observe. The center of those atoms beyond these 4 atoms will be identical to the center of the atom that we see, and the atoms beyond it will also have the center of the its position identical to the atoms that we see. So what essentially we see is, when we look along this direction in red, we see just one plane, and all the subsequent planes of atoms, their arrangement are similar to that of the plane that we see. So if I designate my plane as A, all the planes behind me, the atomic arrangement of all the planes behind me are of the same way, or is the same like the one that is before me. So therefore it will also be as it can also be designated as A, and so on and so forth. For all the planes that I consider, the atomic arrangements in the given plane will be the same. So therefore the arrangement of the atoms along this plane in this direction can be represented by a same letter, same alphabet. It can be referred to using the same alphabet, using the same nomenclature, and this is what we refer to as the stacking sequence. So we will consider more on the stacking sequence in the subsequent lectures. Goodbye.